Okay, we're about ready here, I think. Thank you. So I get to introduce Sean tonight. So who is Sean Carroll? Basically, I want to characterize him as a public intellectual. He happens to be a physicist, a theoretical physicist at Caltech. But if you haven't seen him on something, then you haven't been looking. He's got a great blog, which I have listed in your program. He does another blog. There's one there. He does another one that Discover Magazine hosts called Cosmic Variance. He's been on the Colbert Report, and as a matter of fact, the vibes are here. He was on Colbert last night. I don't think they see it. We won't see it here until next week, I don't think. But anyway, he was there. He had to fly in today from New York because he was on Colbert last night. So, I mean, anybody who's been on Colbert Report has to be important, right? So, anyway, so that's cool. So he's also been, those of you who watched the series Through the Wormhole, hosted by Morgan Freeman. There's a whole series of that. So Sean's in that a lot, talking about theoretical physics and cosmology and so forth. The Teaching Company. If you guys don't know about the Teaching Company, it's called the Great Courses series. Yeah, okay, a lot of people, some fans there. I'm a big fan of this too. I've done like 25 of their courses. You get them for, I don't know, they say they're $275 on sale for $35. So I don't know. Some psychology of that. But they're very good. They find the top professors, the best presenters who've published and respected their colleagues, and then they give them a framework, like here's your best idea, here's the argument, they make them put together their lectures in a very formal way. So you get a series of lectures that are like 30 to 45 minutes each, about 30 or 40 lectures on a particular topic. They're really great. Anyway, Sean did one already on dark matter and dark energy, and another one's in production on the nature of time. I also mentioned, I didn't mention before, the reason I had my eye on Sean last year, and we didn't get him in, and I was looking for him for this year, and then the Higgs thing came off. He's got a new book out, but his previous book, called From Eternity to Here, Looking at the Nature of Time, is one of my favorite popular physics books right now. And I just say, I didn't really agree with his solution to the problem of time, but his critique, his analysis is, in my opinion, my expression was the most honest and high integrity presentations of the physics and everything goes with it, and I assume that he's going to give us that tonight with the Higgs boson. There's a lot of fluff out there in physics. We're off by 10 to the 120th on the some factors here. Anyway, I really recommend that book, and I recommend Sean Carroll, and thank you to Sean for taking the time to do all this presentation to the public. And so with that, Sean Carroll.
Can you guys hear me from this microphone? Is that okay? Yell if you cannot hear me. I know it's a difficult thing. So it's great to be here in Portland. Great to be talking about this topic. It's only after my book appeared that I realized that all of my book titles come from disturbing somebody else's book title. Obviously, this is borrowed from Douglas Adams' The Restaurant at the End of the Universe. I have to explain to people that the Higgs boson is not literally you don't go to the end of the universe and see the Higgs boson there. It's a metaphor. That's okay. We'll try to explain what that's all about. And the best place to start is Independence Day this year, July 4th. I spent my July 4th weekend in Geneva, Switzerland. These guys here are camping out overnight. It's very much like you would see people camping out for the new iPhone or a rock concert or something like that, except there's a lot more laptop computers. And what were they camping out for? It was not for the Led Zeppelin reunion. It was for some PowerPoint presentations that happened the next day. Here's the lecture hall, and these guys are going to give their PowerPoint presentations about a new particle called the Higgs boson. And for the last 6 months, we particle physicists have been trying to explain what is the big deal with this Higgs boson. Why was it something that caused so much excitement, people camping out overnight just to see some technical talks? It's very hard to explain in 30 seconds what the Higgs boson is, so I'm very glad that I have more than 30 seconds to do it. A typical way to explain particle physics is to go back to this guy. Does anyone know who this is? Anyone recognize this? Well, if you look up in the catalog, this is called Democritus. Democritus is the Greek philosopher 2,500 years ago who is, in some sense, the first particle physicist. He was the one, and his teacher, Leucippus, whose all of his works are lost, but he was the one who first said in a very popular way that everything we see around us is made of individual particles. It's just arrangements of the different particles give rise to all the different kinds of stuff that we see around us. He didn't call them particles, he called them atoms. We got a little overeager in the 19th century, and we gave the name atoms to things that in fact are not elementary particles. We now know that what we call atoms have subparticles, but what Democritus was really talking about was the very idea that water and air and earth are not fundamentally different things. They're just different arrangements of the same kinds of things in different combinations. And in that, he was completely right. And the 19th and 20th century have given us this triumphant vindication of that idea. He also, because it was a long time ago and the modern university had not been invented yet, philosophers were allowed to talk about more than one thing. So in addition to talking about natural philosophy, he talked about ethics and morality and so forth, and he was a very optimistic guy, and he was given the name the laughing philosopher. So he lived 2,500 years ago. No one has any idea what he looked like, but his nickname was the laughing philosopher. So in the Renaissance, he was a very popular subject for portraits, because this one is by Rembrandt. You would just paint a portrait of yourself laughing, and then you would call it Democritus, and people would buy it. But in fact, despite all the good ideas that Democritus had, I do not want to begin with that particular slant on what we've learned, because the reason why the Higgs boson in particular is so difficult to explain is that the particle that we think we found, which we have, a new particle of nature, but it's not the particle that is that important. What's important about the Higgs boson is that it is a manifestation of something called the Higgs field, an invisible energy field that fills this room and every part of the universe that we can see. Empty space, the middle of the earth, the sun, the moon, the stars, they're all swimming through this invisible field called the Higgs field. So it's really field theory that we need to understand. In fact, quantum field theory that we need to understand. So I'm very glad that Terry invited me to give this 20-hour-long talk so that you can really get some of the basic flavor of quantum field theory. But, well, let's start with, rather than starting with Democritus, which is a little pretentious, let's start with these philosophers of the modern era. This is, these guys are called the Insane Clown Posse. This is Shaggy 2 Dope, and that's Violent J, not the names that their mothers gave them. But they are a popular hip-hop group, and they caused some controversy a couple of years ago with a new song and video called Miracles. And their song, it was controversial for more than one reason. For one thing, it was not nearly as, violent and party-centered as their previous ones. It was about, the awe and love that they have for the universe. But it also tended to rub scientists the wrong way a little bit. So there was this verse, I see miracles all around me, stop and look, it's all astounding. Water, air, fire, and dirt, frickin' magnets, how do they work? Frickin' was not the word that they used there. You can look it up on the internet what the word was. But so this rubbed people the wrong way for a couple reasons. For one thing, dirt and work just don't rhyme. For another one, magnets, we totally know how magnets work, okay? You're a recording artist, your songs appear on media with little magnets in them. It's very important that you recognize that magnets are within our wheelhouse in terms of stuff that we understand. But having said that, I want to point out that even though we do know how magnets work, it is nevertheless astounding. They were right about that. Magnets, even though we understand how they work, should not be taken for granted. Think of what happens with a magnet. You can stick it on your refrigerator. That's a typical thing you would do with a magnet. Well, you can stick a piece of tape on your refrigerator as well, but there's a difference. The difference is that the tape you need to touch to the refrigerator to make it stick. But the magnet, if you hold it very close, you can feel it pulling on the metal in the refrigerator even before it touches it. The magnet reaches out across the distance between the magnet and the refrigerator to somehow exert a force. How does that happen? That is actually a very good question, and it's not just these modern-day intellects that were astounded. Here is a predecessor of the Insane Clown Posse, Isaac II Newton, Sir Isaac, and he invented something called gravity. Of course, he didn't invent gravity. We knew about gravity all along. But Newton invented a theory for how gravity works, a theory that unified the operation of gravity here on Earth with the performance of gravity out in the sky as well. And according to Newtonian gravity, there was a simple rule that the further away you get from an object, here's a big object like the Earth, and it's pulling on something small like a baseball or something like that with the force of gravity. And Newton says that the further away the thing is, the less gravitational pull it feels from this massive object, the Earth. In fact, it goes as 1 over the distance squared, the famous inverse square law. The gravitational force is 1/4 the size when you get twice away. So this big arrow means that the force is strong, the little arrow means the force is relatively small. And the wonderful thing about Newton's theory is it fits an enormous amount of data. Today we can do better. Einstein came up with an even better theory. That's how science works. But Newton's theory is awfully good. You can get to the moon with Newton's theory, and in fact we did. On the other hand, people did not immediately accept it. It was controversial, and not because it didn't fit the data, but because people thought it didn't make sense. You should have theories that not only explain the data, but also theories that make sense. That's a perfectly respectable thing to demand. And the problem with Newton's theory is that it involved what is called action at a distance. Just like that magnet pulling on the refrigerator, Newton's theory imagined that the Earth pulls on distant objects with a certain force, even though there's nothing in between the objects. Over a distance, this force is acting, and people were very confused by that. How could that be possible? Newton himself didn't like it very much. In fact, he said it was sort of intellectually disreputable, but it fit the data, so, you tell me what's going on. So this guy told us what's going on. Pierre-Simon Laplace, an 18th and 19th century mathematical physicist, came up with an idea. Now, he doesn't get credit for inventing a new theory of gravity because the theory he invented is exactly the same as Newton's theory. What he came up with is a better way of thinking about Newton's theory of gravity. Laplace said, imagine that the space in between the Earth and the distant objects is not empty. Imagine that there is something in empty space that you don't see called the gravitational field. The gravitational potential field in particular. And so what this graph is supposed to show is that the field is very low here, and then it rises up here. But it rises sharply if you're near the Earth, and then it fades away to a more flat behavior further away. And what Laplace pointed out was that this field obeys an equation that is equivalent to Newton's equation, that the gravitational pull on something is just the slope of this field, how fast it's tilting downward. Here, where it's tilting downward quite fast, you feel a strong gravitational force, and there you feel a weaker gravitational force. It's exactly the same predictions as Newton's theory, but a better way of thinking about it, that there is not action at a distance because the Earth is not pulling directly on this object far away. The Earth is affecting the field in its vicinity. And that's affecting the field in its vicinity, and then that's affecting the field there and there and there, and you work your way out through space. There is no action at a distance. Everything is local, and that's how the universe works, according to Laplace. It turns out that Laplace was onto something very big, that in fact everything in the universe is made of fields. That is the modern way of thinking about the universe at a fundamental level. In some sense, a field is the opposite of a particle. These pictures look almost reminiscent of each other, but this picture is a picture of tracks of individual particles passing through a bubble chamber, a cloud chamber, leaving little wakes, so you see some particles just go left and right and some curl around. So a particle has a location. A particle, what we would think of as an elementary particle, has 0 size, but it has a location in space. A field is everywhere. It has every location in space. But at every location, it has a value, and that value might have a direction also. So these are the lines of force around a magnet, tracing out the magnetic field that is everywhere around the magnet. That's the easy part. Particles over here, like electrons or protons. Fields over here, like gravity and electromagnetism. You think that makes sense. But there's this puzzle that physics students learn about when they're young. The electron, the photon, these particles that we talk about sometimes they have wave-like behavior. Is light, Newton wondered about this, is light really particles or waves? So the answer in the modern perspective comes from quantum mechanics. Quantum mechanics is our best theory of how the world works at very, very small scales. And all you need to remember about quantum mechanics for the purposes of the next hour is this little motto. When you think about what really exists, it's fields. When you look at the fields closely, they look like particles. That's what quantum mechanics says. So quantum mechanics says that you have these waves passing through reality, whether it's the electric field, the magnetic field, the gravitational field. But when you look at it closely, you see individual particles. This is the XKCD cartoon. They're looking at the amber waves of grain, but they say, well, when we observe them, they become amber particles of grain. And that is right, if you're able to observe them quite closely enough. Here's another illustration from David Deutsch, a quantum physicist who wrote a wonderful book called The Fabric of Reality. And he points out that if you were a frog, you could see individual particles of light. Not because frogs are excellent at doing quantum mechanics, just because frogs have slightly more sensitive vision than we human beings do. So you imagine someone with a candle or a torch or a flashlight walking away from you. You see this light getting dimmer and dimmer and dimmer, right? Because they're getting further away. But if you had perfect vision, or even vision as good as a frog, you would see that eventually the light doesn't get dimmer anymore. Instead, it just starts flickering on and off as the person gets further and further away until it's almost always off with an occasional small flash of light. That's because that frog is seeing individual photons. Light can be thought of as a wave in the electromagnetic field, but if you look at it closely enough, what you see is individual particles called photons. So that's the answer to this question. Is light a particle and a wave? It's a wave. That's what it is. But when you look at it carefully enough, you see individual particles called photons. And the same thing is true for what you think of as regular old particles, electrons, quarks, protons. These are all waves that when you look at them closely enough, they look like particles. And this subject is quantum field theory. It is the central way of thinking about the world according to modern physics. It's easy to Google books on quantum field theory, and there's a bajillion of them. And yet, we don't talk about quantum field theory in popularizations. We talk about quantum mechanics, we talk about particle physics, we talk about relativity. For that matter, we talk about string theory and the multiverse and so forth. We talk about time travel and extra dimensions. But quantum field theory, we say, well, that's too complicated, they don't need to know it. That was true until July 4th of this year. You didn't need to know it. But now you need to know it. Because to understand what the Higgs particle, the Higgs boson, is all about, to understand why it's so important, you need to understand that what the Higgs boson is a little vibration in something called the Higgs field that fills empty space. So let's think about where particle physics had gotten to. And, I will use the sloppy language that every person in the universe uses, which is, I will call the electron a particle. But you now are a sophisticated audience, and you know that when I say the electron is a particle, what I mean is it's a wave, and the individual vibrations in the wave show up as particles, right? You got that. Good. Here was particle physics, circa 1935. You could forgive physicists of the 1930s for thinking that they almost were done, that they almost had it all. There was a few I's to be dotted, a few T's to be crossed. We had discovered these 3 particles, the proton, the neutron, and the electron, and together they made atoms. This is a hydrogen atom with an extra neutron there, so what's called a deuteron, or a deuterium atom. So one proton, one neutron, and one electron. And there were three forces that acted on these three particles. There's an electromagnetic force, that's what holds the electron to the proton. There's a nuclear force that holds the neutron to the proton. And there's the gravitational force that just pulls everything together. So it pulls the whole atom down to the Earth, for example. And there's just a few little things we didn't quite understand, like radioactivity, that we want to understand a little bit better. And of course, whenever there's one little thing you don't understand, it blows up in your face. But we have a slightly more complicated picture of the world now, but it's still pretty manageable. For one thing, there are four forces, not just three. We divided the nuclear force into the strong nuclear force and the weak nuclear force. And there's one more particle called the neutrino. So the strong nuclear force is what holds the nucleus together. And inside that nucleus, it's not protons and neutrons, it's quarks. They're up quarks and down quarks that make up protons and neutrons in different combinations. But sometimes a proton turns into a neutron, like in the sun. You know, the nuclear power that powers the sun and makes it warm outside. That's what happens in Los Angeles. I'm not sure about Portland up here, but there's this thing that shines in the sky and makes it warm during the day. That's the weak nuclear force at work, and it spits off a new particle called the neutrino. So that's not so bad. Instead of 3 particles and 3 forces, there are 4 particles and 4 forces. The weird part is that these 4 particles, electron, down quark, up quark, and neutrino, make a family of 4 particles, and there are 3 families in total. So there's 2 duplicates of this simple system of just 4 particles. So there's 12 particles overall, and that makes no sense to anybody at all. So this is a great theory. It fits the data, but it leads to bizarre, terrible flowcharts like this one. So if someone tells you that you're an elementary particle, you can figure out which one you are by asking, well, are you a boson or fermion? What do you feel? And blah, blah, blah. And this whole picture is called the standard model of particle physics, I guess because the marketing director of particle physics didn't want people to think it was very interesting. But it is very interesting, the standard model. It is the best theory ever devised by physicists. The particles that we have, or the fields, to use sophisticates, come in 2 different kinds. If you take up space, an electron cannot land right on top of another electron with exactly the same properties. That means the electron is a fermion. It takes up space. A photon can sit right on top of another photon with exactly the same properties. So photons are bosons. They can pile on top of each other. So bosons give rise to forces of nature because the gravitational force that is pulling me down to the Earth right now is caused by many, many, many gravitons piled on top of each other. The reason why I don't fall through the stage into the center of the Earth is because I have electrons in me and the stage has electrons in me, and they take up space because they are fermions. So fermions are the matter particles that make up stuff. Bosons are the force particles that hold things together. And there are weak interactions, strong interactions, electromagnetism, gravity. And then there's these simple particles that we know, electron, its neutrino, the up and down quarks, and there's another generation, another family, and another family on top of that, again, bizarre and unexplained as of right now. And then way up there in the corner, there's yet another thing called the Higgs boson field that we need to understand. So where did that Higgs boson field come from? It was back in the 1950s. We had the particles, we had a couple of forces that we think we understood. We had gravity, Newton and Einstein gave us that. We had electromagnetism, that was figured out at the classical level in the 1800s. And then in the 20th century, we learned to quantize it. People like Feynman and Schwinger won Nobel Prizes for understanding quantum electromagnetism. So Yang and Mills, this is C.N. Yang and this is Robert Mills, this is long after 1954. In 1954, they were about 30 years old, they were young guys, and they tried to say, well, we're going to try to explain the nuclear forces, the forces that are going on inside the nucleus. Maybe they're just like electromagnetism, only a bit more complicated. That's a very natural thing, it's a very physicist kind of thing. Let's start with the thing we understand, complicate it up a little bit, and maybe that will give a better theory than we have yet. The problem is with the magnets pulling on the refrigerators, that the electromagnetic force, just like gravity, extends across macroscopic distances. But the nuclear force is short range. So if nuclear forces were just like electromagnetism, you would naively predict that they would extend over very large distances. That's the field-centered way of saying it. The particle-centered way of saying it is the bosons that carry the nuclear forces, if they were massless, like the photon and the graviton that carry electromagnetism and gravity, then the forces would extend over a long range. So if you give them a mass, you could explain why they're stuck in very short distances, but that is not like electromagnetism. So let me take away all these scary words and just show you a picture. The long-range forces that we understood, gravity and electromagnetism, you have some object that gives rise to forces, and the lines of force extend out forever. They dilute away as you get further away, which is why the force gets less and less strong, but they don't ever end, these lines of force. Whereas for the nuclear forces, the lines of force extend out a little way and then they end. They dilute away and they just stop going. This is what the forces seem to do experimentally, but not what Yang and Mills would have predicted. So they were not taken very seriously within the physics community. They were right, however, so they had the last laugh. Yang and Mills were absolutely right. Both the strong force and the weak force are just more complicated versions of electromagnetism. But they're complicated enough that they behave very, very differently. And just to give full employment to physicists, the strong nuclear force and the weak nuclear force behave differently in utterly different ways. The strong nuclear force, the bosons that carry the force, are massless, but the force is so strong that they don't ever leak outside the proton or the neutron. This is a phenomenon called confinement. Here is a proton. You have all these little quarks inside. They're held together by gluons. And those gluons just keep attracting each other. The reason why the strong nuclear force doesn't extend for a very large distance is because the strong nuclear force itself won't let it. It binds itself inside these particles and we never see them. This was figured out by these guys in the early 1970s, and they won the Nobel Prize in 2004. The weak nuclear force required more effort to get it right. And the answer for why the weak nuclear force does not extend over an infinite range is something called the Higgs mechanism. Why? Because Higgs was one of the 8 people who invented it. And he has the coolest last name, so he gets his name on the mechanism. So Philip Anderson is a guy who already has won the Nobel Prize. He's a condensed matter physicist. Engler and Brout were friends who wrote a paper saying how to make the weak interactions make sense. Here's Peter Higgs visiting the Large Hadron Collider. Kibble, Guralnik, and Hagen, some Americans and Brits that work together. Glashow, Weinberg, and Salam already won the Nobel Prize. Here they are ready to receive their prizes from the King of Sweden for putting the Higgs mechanism to work in the weak interactions. And it was Gerard de Tooft who also won the Nobel Prize already for showing that the weak interactions with the Higgs mechanism make mathematical sense. So that's not meant to explain anything. I just want to show the pictures of the people doing it because this advance in physics was not like Einstein, the lone genius, coming up with general relativity. This was something that was put together over a series of years by many different people. Each one of them get a little bit closer to the perfect answer. None of them got all the way there all by themselves. It was very much a team effort, which is good. That's how science usually works. It's bad when you come to giving out Nobel Prizes, and we will get back to that. The upshot is that the W and Z bosons, which carry the weak nuclear force, are massive. Unlike the photon, the graviton, the gluon, unlike all the other bosons that carry forces, the W and Z bosons are massive, and the reason why is this thing called the Higgs mechanism. So what is the Higgs mechanism? What these guys said is that, well, maybe empty space is filled with an invisible energy field that you can't see. It sounds like an attractive idea, but remember, everything is a field. The difference is that the Higgs field is not zero even when space is as empty as it can possibly be. So if you go out there to interstellar space and you make a completely empty little region of space, you imagine there's no gravitational field, no electromagnetic field, no matter, no dark matter, no nothing. It's empty. What that means is that all of the fields of nature are sitting quietly at zero, or maybe oscillating just very slowly around zero because of quantum mechanical uncertainties, except for the Higgs field. The Higgs field is stuck very, very far away from zero, even in empty space. So here's my best attempt at showing you what that means. Here's the value of a field, and here's where you are in space. And most of the fields in the universe, the electromagnetic field, the gluons, the quarks, etc., they're all just jiggling because of quantum mechanics very, very close to zero. The Higgs field jiggles because of quantum mechanics, but not near zero, near another value somewhere way out here. And a Higgs boson particle is a big vibration in the Higgs field. So what all those guys in the previous slide were saying is, maybe there's a field that suffuses all of space that affects how the weak nuclear force propagates from place to place. So in other words, the reason why, I don't know if you can see this, is supposed to be like a shaded thing representing the Higgs field filling space. The reason why the weak nuclear force doesn't extend that far is because it's eaten up, it's absorbed by the Higgs field all around it. So that was an idea, and this is just like, it's easy to let this slide by, so I want to emphasize it. Here's an idea that a bunch of guys came up with in the early 1960s. Why? Because they had this other idea that maybe the weak nuclear force is like electromagnetism, and they couldn't get it to work, and they were grasping at straws, and they said, maybe all of space is filled with this field, okay? And other people said, well, how would we ever know that? And they said, well, if you poke at the field and make it vibrate, there'll be a new particle. You should go look for that particle. And almost 50 years later, $9 billion, thousands of people working over the course of decades, we found it. We found exactly what they predicted. They turned out to be right. And it's just their human brain was able to reach across the possibilities and figure out how nature really worked. As a bonus, not even planned by the original thinkers, but this also explains how the particles that make up you and me get their mass. So not only the W and Z bosons, which carry the weak nuclear force, but the electrons and the quarks that make up your atoms, they also get mass because they move through a Higgs field. You can think about waving your hand in empty space and there's no resistance to it whatsoever. If you wave your hand through molasses, you feel a force. It takes more effort to move your hand, right? So that's like an electron moving through the universe. If it weren't for the Higgs field, electrons would have no mass. They would always move at the speed of light. With the Higgs field, the electron keeps pushing against the Higgs. It becomes massive and it moves more slowly. And you might say, well, I'm not that interested in how fast electrons move, but you are. Because your atoms that make up you are these little nuclei that don't do that much, and then these electrons around them. And if it weren't for the Higgs field, the electron would have no mass and you wouldn't be able to make an atom. Because the electron would always be moving at the speed of light. It would never settle down and sit inside an atom. And if there weren't atoms, there wouldn't be molecules. And if there weren't molecules, there wouldn't be you, or me, or any of your best friends or worst enemies. There wouldn't be anything interesting in the universe. If it weren't for the Higgs field, we would just have these electrons zooming around at the speed of light. There could be no complex structures, no life as we know it. So this Higgs field is doing a lot of work. Or at least that was the idea. So let's go look for it. So we built this thing called the Large Hadron Collider. It's the world's largest particle accelerator. It's also the world's largest machine, the most complicated machine ever built. It sits outside Geneva, Switzerland. It's part of CERN, a European particle physics laboratory. And it's underground. It's 100 meters underground. If you were walking on top of the ground, there'd be cows and farms and quaint French villages, and there'd be the Alps in the background. But it goes around for 17 miles around underground. And you can see there's, it's going underneath houses and things like that. It cost about $9 billion. There's approximately 10,000 people associated with either building it or doing the experiments. What the Large Hadron Collider does is take protons, the little particles that are inside your nuclei, takes individual protons, and it accelerates them to close to the speed of light, to 99.999999% the speed of light. Why? To give them a lot of energy. And then it smashes them together with this enormous energy, and out of that energy you can make new particles, like the Higgs boson. So just to give you some of the crazy numbers, there's 6,000 tons of magnets cooled to a temperature colder than the temperature of outer space. It is also a better vacuum than outer space is. And the amount of cable inside would wrap around the equator of the Earth almost 7 times. It's a complicated, messy thing. Took a long time to build. Here are the 2 people who probably deserve the most credit. Carlo Rubbia, who's already a Nobel Prize winner himself. He was the guy who discovered the W and Z bosons. And he was the one, he's an outsized personality, and he pushed Europe to get together to donate their money to build this enormous machine to look for the Higgs boson and other particles. Here in the United States, we had a machine, the superconducting super collider, but we didn't have Carlo Rubbia, and we lost. We turned off our machine halfway through building it. We said it's not worth the money, and we closed it down. So the Europeans went forward, and they nominated this guy, Lyn Evans, who's a Welsh physicist, to shepherd the project, and he's been the project leader of the Large Hadron Collider from when it started to today. So he's the one who really made it happen in various ways. And at this point in the talk, I want to stop talking about physics to give you a small editorial comment, because I love showing the pictures of the human beings who did this, because the science itself is universal, but it doesn't just happen. It's work done by actual human beings. But when you're talking about the history of a science like physics, those human beings are almost all guys. They're almost all men. And there's a reason why they're almost all men. And the reason why is because women have been subjected to systematic discrimination in science for hundreds of years now. And so I just want to make the point, thank you. I want to make the point that this has been going on, it still is going on, and also that it is changing. So that so let me show you. Since I'm a scientist, I like showing graphs. So here's a study that people did. They gave a job application to scientists, and they said, rate how good this job applicant is. And it was exactly the same application, except on some of them the person's name was John, and on some of them the person's name was Jennifer. And when the person's name was Jennifer, they were always ranked lower in competence, hireability, and mentoring, and how much you would pay their salary. And number 1, this was by both men and women. And number 2, this is a 2012 study. This is not, the 1950s, Don Draper, Mad Men, sexism. This is what people who are in charge of the scientific establishment now believe, that if your name is Jennifer, you're not as competent even if you have exactly the same set of skills as if your name is John. The good news is that it is changing, and it is changing dramatically. This is the percentage of women getting bachelor's, doctorates, and postdoctorate degrees in physics, and it's going up from 5% bachelors in 1968 to over 20% in the most recent years. And it's not because the genetic makeup of girls got smarter by a factor of 4 over the course of these decades. It's because, and it doesn't happen by itself, it happens because people fight against the entrenched biases and they point them out. And so even though when I show you pictures of the greats from the history of physics, they're all guys, the future history of physics is going to look a lot more diverse. Okay, so now we know that. Now, all of the guys and gals who built the Large Hadron Collider faced challenges. It is not something that they teach you in graduate school when you're learning your quantum field theory, how to build the world's largest machine. Here's a picture of a relatively small part of the Large Hadron Collider wending its way through the streets of a tiny medieval village in France. Many of the pieces of the LHC are the size they are because that's how big the streets were that they knew they would have to go through. Then they dug these tubes and so they could lower down these giant magnets. And when you dig these tubes, remember, you're in France and Switzerland when you're doing it, so the first thing they do is they hit a Roman ruin. So the physicists are kicked out and the archaeologists are brought in, and for 6 months we're not allowed to do anything but dig up coins and pottery. And then you can say, all right, keep going now. So you keep going, and then they kept going, and then they hit a river, an underground river they didn't know about. So bless their hearts, they were physicists. They flooded it with liquid nitrogen to freeze the river, dug it out, put the tube down, and let the river flow around them once again. $9 billion. This is why it costs money. And then they put the whole thing together, they turned it on, and it exploded. This is an event that happened in September of 2008. It was the press release that went out said that we had a leak. It was actually an explosion. There was nobody down in the tunnel at the time. If there had been, they would have died. 6 tons of liquid helium flooded because there's a superconducting magnet and it heated up and it was bad. But in a sense, it was good because that it gave the people making the collider a respite. They went in, they figured out what the problem was, they fixed every darn magnet down there, all 6,000 of them, and when it came back a year later, it was better than advertised, and it's been going great guns ever since. Around that ring, that 17 miles, there are several experiments. 2 of them are looking for the Higgs boson and other particles, 2 huge experiments, one called Atlas and one called CMS. They both look like spaceships, and they're both very big. To show you how big they are, I've circled the people. There's a person, there's a person. These are not things that you build in your high school physics class. These are different pieces put together. There's over 100 countries involved in each of these collaborations. Both of them involve over 3,000 physicists. So when a paper is written by CMS or Atlas, it has over 3,000 authors because they all, they painted that thing red, and they're now an author on CMS. You collide protons together, over 100 million collisions every second. If you actually took all of the data created by the LHC and wrote it to a disk, your disk would be the largest database in the universe within a second. So, or at least on Earth. I shouldn't say the universe. I shouldn't exaggerate. Who knows what the largest database in the universe is? What you do is you throw away almost all the data. You have incredibly sophisticated computers looking at the events that you get when smashing particles together, and almost all of them are boring and predictable. You throw those away. You keep the ones that might be telling you something new. So it's the result of these experiments that we heard from on July 4th. Fabiola Gianotti is the boss these days of Atlas. Joe Incandela is the boss of CMS. But they're really democracies. They vote, and the term of what's called a spokesperson is 2 years. So these are not, the kings and queens of the experiments. They are the leaders, the spokespeople for the 2 years, and they were the leaders when the Higgs boson was discovered. Just to show you that not everything is humongous, this little thing that looks like a fire extinguisher is where the protons come from. So hundreds of trillions of protons are zooming around the LHC at any one time, but in that canister, there's way more protons than that. This is a canister of hydrogen. There's enough protons in that canister of hydrogen to power the LHC for over 10 billion years. So protons are not the limiting resource when it comes to the LHC. What do? We take these protons, we zap them with electricity, we separate them from their electrons, we accelerate them to this amazing speed, we smash them together, and we see what comes out. So this is data, this is not a simulation. This is what it looks like. Many things come out, and you pick out the events that look promising. Here, 2 electrons came out back to back, and 2 muons came out back to back. That is exactly the kind of thing you might expect if in that little central region, your collision made a Higgs boson, and the Higgs boson decayed into these electrons and muons. The problem is, there are other ways to make electrons and muons at the Large Hadron Collider. So here is what you often say. You often say, we understand what the Higgs can do, so you smash protons together, you make a Higgs boson, and then it decays. And it can decay into different things: quarks, W bosons, gluons, photons. Quantum mechanics says you never know for sure what will happen. You only predict the probability that something happens. And every one of these things that can happen if you make a Higgs boson can also happen even without making a Higgs boson. So people say it's like looking for a needle in a haystack, but that's not actually the right way to think about it. It's like looking for hay in a haystack. We're looking for events inside the detector that could be from the Higgs boson or could be from something else. It's like going through that haystack and finding that there's slightly anomalously more stalks of hay at a certain length than you would otherwise expect. That's what you're looking for, that there's slightly more events with 2 electrons and 2 muons than you would otherwise look for. So here are the money plots that came out of the 2 experiments. Here's ATLAS, here's CMS, and what you're plotting here are events where 2 photons come out with enormously large energy. Here's the number of events that you saw, so a few thousand at every energy, and it's decreasing as the energy gets larger. And there's a bump right there, and you can see it because someone drew a red line through it. Without that, you wouldn't see it. I put a big blue arrow over it just to make it even clearer. There's a bump in both of these experiments at the same place. That means that you found the extra hay in the haystack. You have found more events of this form, where 2 photons come out with this energy, than you would otherwise expect. Why would that happen? Because there's a particle with exactly that mass that is decaying into these photons. So these bumps have been statistically analyzed within a whisker of their lives. They are real. They are not just random fluctuations. There's 2 experiments that don't talk to each other that both get the same result. So there's no question at this point we've discovered a new particle of nature. So to get the mass right, 1 GeV is about the mass of a proton. These plots look a little, scary and technical. So when I wrote the book, The Particle at the End of the Universe, my publisher said, we really shouldn't put those in. They're too scary and technical. And I said, $9 billion we paid for these plots. We need to put them in the book. So they're in there. Well, you see a bump. You see that bump means there's a new particle messing with you, but is it the Higgs boson? Is it the right particle? Is it the particle that we've been hoping for? So you don't only look at photons coming out, you look at all sorts of things. And these plots are too complicated to be in the book, but you guys are now sophisticated, so I can show them to you. This dashed line where it says +1, and this green line right here, this is what you would expect if the particle you're looking at truly is the Higgs boson. And these horizontal lines are the rate at which different things are happening. So here's bottom quarks being created, tau leptons, W bosons, photons, Z bosons. And what you see is that everything centers, there's a little bit of uncertainty in every measurement, but all the different measurements line up on average right where you would expect if this particle that you are creating that was making that bump for you is really the Higgs boson that those guys thought of 48 years ago. So we think that there are Nobel Prizes coming very soon. We found a particle of nature. It looks like the Higgs boson. By the way, we don't want it to be the Higgs boson that was predicted 48 years ago, because it's always more exciting to be a little bit wrong. That's what drives the science forward, is if we learn something by doing the experiment. So far, it looks like the experiment is just telling us that our theory is right. That is certainly worthy of a Nobel Prize. In fact, it's worthy of several Nobel Prizes. The problem is that there's a tradition within the science Nobel Prizes that they are given to individuals, not to groups, and that the individuals have to be 3 of them or fewer. You cannot give the Nobel Prize to 6 people, but it was 6 people who really get credit for inventing the Higgs mechanism. So it's very unclear what will happen with that. For those of us, the many thousands of physicists who have no chance of winning the Nobel Prize for discovering this, the rest of us are trying to do work with it. The Higgs boson is the end of an era. It is the completion of the standard model of particle physics. It is also the beginning of an era. When you compare the Higgs boson to other particles, it is more sociable. It interacts more readily. What we're hoping is that we will use the Higgs that we've discovered as a tool to look into the parts of the universe, metaphorically speaking, that we have never yet seen before. We know that the standard model, even though it's right, is not the final answer. Here, I give you a short version of a theory called supersymmetry. It is the most popular theory on the market for going beyond the standard model of particle physics. And in a word, it says that there are twice as many particles as you thought there were. For every boson in the standard model, the gluons, etc., there is a fermion superpartner. And for every fermion in the standard model, the quarks and the leptons, there is a boson superpartner. This will be a wonderful idea if it is true. So far, there's zero evidence that it is true, but it's still an awesome idea. So we're hoping that we know that the LHC is going to shut off in January. It's going to be quiet for 2 years while the technicians go down and upgrade everything about it. It's going to come back in 2015 at a higher energy. So we're hoping that at that higher energy, we begin to see some of the glimpses of this new world that the theorists have predicted. Notice also that in supersymmetry, there's not one Higgs boson, there are 5 of them. So it might be that we haven't just discovered the Higgs boson, we've discovered 1/5 of the Higgs family, which would be awesome. The other thing we know, of course, is that there is dark matter in the universe. The universe that we see around us is not the whole thing. The astronomers have told us that there is much more matter than can possibly be accounted for within the standard model of particle physics. So ideally, we'll make that dark matter at the LHC, or if not, we might be able to detect its influence once we measure the Higgs boson properties more carefully. All of those little horizontal lines lining up near the Higgs prediction, if one of them is off a little bit, that could be a sign that there's another particle getting in the way or enhancing the rate, and that might be related to the dark matter. This is an actual map based on data of dark matter in a particular region of the universe. We know it's there, we just don't know what it is. But back here on Earth, let's not, be so quick to race out there and celebrate what we don't know. Let's, take a little bit of time to celebrate what we have done. What the standard model of particle physics is a theory of physics that completely accounts for every particle that you are made of, or I am made of. You can imagine other particles, but you know that they do not play an important role in you or me. Because if they did, they would have to interact with the particles we are made of, and we would have noticed that at the LHC and in other physics experiments. When it comes to the stuff that makes up tables and the Earth and viruses and puppy dogs and stars and planets and moons and people, we are done. We have the description of that. It's the standard model of particle physics, quarks and leptons with mass from the Higgs field interacting with these 4 forces. In the 2,500-year-old project to understand the world we experience every day, the easy part is now over. The hard part is staring us in the face. What is the dark matter? What happens inside a black hole? Why is there more matter than antimatter? What about, subsets of physics like chemistry and biology and economics? What about all that stuff? We have a long way to go. There's plenty of science that is ahead of us. The easy part is now over. So that's the point of this discovery that was made. It was something that it took almost 50 years to get it right, but it is the culmination of really hundreds of years of thinking about this stuff. It is the end of a very, very tiny subset of the kinds of questions that scientists like to ask, but an important subset, understanding the particles that you and I are made of. From now on, 1,000,000 years from now, people will talk about particle physics pre-Higgs boson discovery and post-Higgs boson discovery. That has been the big deal. Thank you.
Okay, go ahead. Maybe quiet down a little bit.
So you said that the electron wave / particle moving through the Higgs field is what gives the electron mass. But photons also move through the Higgs field because they move through space. Why don't photons get mass? Why can they travel at the speed of light at all times?
That's right. So this is a good question. It's a great question. Some of the particles in the standard model, that's what I'm doing. Some of the particles in the standard model of particle physics have mass. Some of them don't. Electrons have mass, photons don't. But they all move through the Higgs boson field. The question is, why do some particles get a mass by moving through that field, and why do some not? And the answer is because just listing the particles is not the end of telling you the standard model. All those particles have different particles they do and do not interact with. Photons, for example, carriers of the electromagnetic force, interact with charged particles but not neutral particles. So they interact with electrons, but not neutrinos. The particles that get mass are the particles that interact with the Higgs boson field. The photon does not interact with the Higgs boson. It goes through uninterrupted, does not get any mass. Likewise for the gluon, the graviton, etc. The W boson, the Z boson, the electrons, the quarks, they all interact directly with the Higgs, and the stronger they interact, the more mass they get.
Thank you.
Yep.
Nobody else.
Just you.
There's been a lot of press over the last decade or so about grand unification theories. You mentioned string theory. Lee Smolin came out with a book several years ago. I think he's now on the senior leadership staff at CERN challenging some of that. How does this affect, if at all, where we're headed in that regard with some of the grand unification theories?
Sure, this is another great question. When, what one does as a working physicist every day is try to move beyond what we already understand. Some of that movement is very, very close to what we already understand. Some of it is an attempt to wildly speculate very far beyond. So the question is, what about these grand unification theories and other very, very sweeping, ambitious attempts to fit all of the particles and forces of nature into a single framework? Well, the thing is that we've known about the Standard Model for years now. The Standard Model was more or less set in stone in the mid-1970s. The Higgs field was part of the Standard Model. It was the part that we didn't know for sure was there, right? So it's very, very important that we found it, that we had evidence for it. But people were trying to come up with alternatives to it, and none of those alternatives were very convincing. And therefore, for decades now, anyone who has tried to come up with a theory of grand unification already has built into it the Higgs boson or something much like it. So the new data we have has not told us anything at all about grand unification or string theory or whatever, because if you had a theory of grand unification that didn't have the Higgs in it, you wouldn't publish that, you would move on to something else. Now we're hoping that changes as we get more data, as we get more precision data. Many theories will be ruled out. Hopefully we'll find more than one particle. Hopefully we'll find new properties of the one particle we have, and hopefully that will push us in the direction of a better grand unification. But we have to wait for the data to say what it will say.
Thank
you. Well, it's in my understanding that energy cannot be created, only transformed. And if the Higgs particle gives all others mass, or certain particles, then what might this mean for the search for the Big Bang, and where the mass and energy might have come from, and how does the Higgs fit into that search?
Yeah, that's a difficult question, which means it's an even better question than the good. The really good questions are the ones I know the answer to, and this one I don't. The question is, what do we learn about things like the Big Bang and the creation of the universe from studying the Higgs field? I mean, the answer might be nothing. The answer might be that there's nothing directly that we learn about this very difficult problem, where did it all come from, just by studying the Higgs field. We're hoping that we get more than that. We're hoping that the Large Hadron Collider might teach us something about supersymmetries, one thing I mentioned, but also extra dimensions of space is something that many more ambitious theories predict and could be detected by the Large Hadron Collider if we get lucky. And even better, we could just be totally surprised by something when we look at even higher energies. But that would be the optimistic take. The pessimistic take is it teaches us something about an energy scale higher than we've ever seen before, but still nowhere near as high as what happened at the Big Bang. I'll let them go first, and I'll go to you. Yes?
So I actually viewed the Colbert Report last night, so I saw you on there.
Excellent.
I was just wondering, did you receive the bump, the Colbert bump?
Yes. So the Colbert bump is much bigger than the bump that you saw here in the data. The Colbert bump is if you plot your book sales versus time, and yeah, totally. It was like 1,200 on Amazon yesterday, and it's like 200 today. So, ooh.
Thank you.
My pleasure. Yes.
So you just touched on this point, but I wanted to ask is there anything we can gain in terms of technology from the Higgs field?
Yeah, I mean, it's a really good question because $9 billion we spent doing this, and the answer is no. But there's two things, there's two little footnotes to that, both of which are very important. One is that, again, let me do it in the opposite order. The search for the Higgs boson has led to amazing technological progress. We had to build the LHC. People have done studies which say when you try to do basic research with absolutely no application in mind, for every dollar you spend, you get way more than $1 back into the economy because you needed to build better superconductors, better information technology, better all sorts of things, and that spreads out everywhere. The most obvious example is a little invention that came from CERN a few years ago called the World Wide Web. The World Wide Web was invented by particle physicists trying to share data back and forth. So it does pay for itself more than once over. The other footnote is that's not why we do it. That's nice, but the reason we do it is we want to understand how the universe works.
Thank you.
Sure.
Now that you found the evidence that you want for the Higgs boson, what other questions are you hoping to be answered by the LHC?
Well, that's great. So the question is, what else can we get from the LHC? And the Higgs boson was the one thing that was almost a no-lose proposition. Either we would find it, or we wouldn't find it, and that would mean that all of our theories were wrong, and we had to tear things up and start from scratch. After that, we have a huge number of speculations, any one of which might come true at the LHC, and we're just going to have to wait and see. Supersymmetry is one example. Finding a particular dark matter particle is another example. Finding extra dimensions of space is another example. Finding an imbalance, something that tells us why there's more matter than antimatter in the universe, that would be very nice. Finding new forces of nature over and above the four that we know and love, that would be nice. There's other puzzles that are lying around. The biggest puzzle that is directly applicable to the LHC is why is the Higgs boson so much lighter than it should be according to certain back-of-the-envelope calculations. So the Higgs is the one thing we knew we were looking for. Now we're stuck with many, many questions and a shiny new particle accelerator, and we're going to hope that it helps us out. Sure.
So the famous Young's two-slit experiment, which
The what?
The Young's two-slit experiment, which demonstrates the duality of matter and wave. The wave-particle duality is demonstrated by the two-slit experiment, Young's experiment.
Yes.
Where it creates interference patterns or not, depending on somebody who's observing it or not.
Right.
How does the standard model explain that?
Oh, that is a pre-standard model question. The question is the double-slit experiment. You pass something, let's say photons, through two slits, and they go on the other side and you detect them. And they're waves, right? It's photons. So you get an interference pattern. If the waves cancel each other out, you get nothing. If they're superimposing and gain, you get a lot. But then somebody sneaky comes along and watches the slits. And they watch which slit the photon went through. Because if you see which slit the photon went through, then it's not a wave anymore. It's a particle. It went through one of the slits, not both. And when you do that, even if you do it very, very gently, the interference pattern completely disappears. There is no more interference once you've turned that wave into a particle. So that is just quantum mechanics. That's not the standard model at all. So the question is, can you make sense of quantum mechanics? And we're trying to do that. Quantum mechanics is in this weird situation. Quantum mechanics is like Newtonian gravity before Laplace. It fits all of the data. It's certainly right in some way, but it's not quite satisfying. We think that there's something missing at a fundamental level. That is, in fact, something that I'm working on myself. I don't think there's any deep barrier. I would say that, we're going to keep thinking about it and we're going to understand it. But as far as predicting the data, we already have that set. Yes.
So about the LHC, it's already going at 99.99999% of the speed of light.
Yes.
So how much farther can you push it?
There's an infinite number of more nines that you could add. You can't get to the speed of light is the thing. So that's just, when you say that the protons are going 99.999% of the speed of light, you're just trying to impress the people in the audience. What matters is how much energy the collisions have. And the energy right now in the collisions is 8,000 GeV. Remember, the energy in a single proton is about 1 GeV. The energy in a single Higgs boson is about 125 GeV. So we have 8,000 GeV, but when you do that, it's not very efficient. You don't just make an 8,000 GeV new particle, so most of it just gets lost. It's not a Prius, it's a gas guzzler, the LHC. So we're going to ramp it up to 15,000 GeV, which is quite a bit more, and hopefully what we will see is a whole bunch of new particles, and then maybe someone will build a better particle accelerator. Let's be honest, if the LHC doesn't find any new particles beyond the Higgs boson, nobody might build another particle accelerator, and we may never discover new particles, and that would be bad.
Thank you.
My question is pretty much twofold. One, bosons all have integer spins, correct? And most of them have around 1 or -1. What are the limits to those numbers? I mean, I've not seen one above, I think, 1 or maybe 2, but do they go higher? Is the limit at like 10? And then how does that play into trying to learn more about gravitons and their properties?
So you've been reading outside of school, young lady. I think that you did not just think of that question here today. So one thing that I didn't mention but is true is when you talk about bosons and fermions, I define them as fermions take up space, bosons pile on top of each other. But every little elementary particle has spin. It's like a top, but it doesn't spin up or spin down as a fixed amount of spin that it never goes away. And for fermions, the spin is either 1/2 or 3/2 or 5/2 or 7/2, etc. It's an integer plus a half. For bosons, it's either 0 or 1 or 2 or 3 or blah, blah, blah. In principle. In practice, as you point out, all the bosons that I listed have a spin of either 0 or 1 or 2. The graviton is 2, the Higgs boson is 0, everything else is 1. All the fermions I list have a spin of 1/2. Now, so can you get bigger numbers? What we currently think, and I can't guarantee this because experiments always decide, what we currently think is that it's easy to get more spin just by taking collections of more than one fermion. So the nucleus of an atom can have a much higher spin than an individual proton or neutron. But the fundamental particles out of which nature is made never have spins higher than 2. That is a theoretical belief. We have little arguments that you can give that if you tried to write down a quantum field theory for spins higher than 2, it would not work. It would not make sense. The universe would just not give you any sensible answers to the questions you're asking. So we both observe and believe that 2 is the upper limit to the spins, but if we find something new, we would have to change our minds. Yes?
I was wondering, with things like electromagnetic fields and electric fields, we can control those, and mass, potentially, if you put two planets together, I guess you kind of create more mass, more gravity. Is the Higgs field something that you could potentially control or manipulate in any way?
Yeah, so this is related to the question of the possible technological applications, and I said no, there aren't any. And the reason why I said there aren't any is because it is very, very difficult to imagine controlling the Higgs field in any way. The Higgs boson itself decays away in about a zeptosecond, which you don't need to know the number, it's really short. That's why when you see these pictures, you're not seeing the tracks of Higgs bosons. The Higgs boson has a track that is unimaginably small in this picture and will never get any bigger. As soon as we make it, it goes away. The Higgs field in empty space, you might say, well, if you could move the Higgs field, from its value in empty space down to 0, remember this value that we had up here, if you could decrease that, maybe something interesting would happen. But it takes energy to do that, and energy means mass. So if you had a ping-pong ball region of space, and inside you set the Higgs field down to 0, that ping-pong ball would have the mass of the Earth. And we don't have the energy to do that. And then it would collapse into a black hole and you would regret having asked the question. So probably not.
So you said this discovery marks the end of an era in physics. Do you think we're ever going to run out of new discoveries to make? And if so, what happens to all the physicists?
This is a very important question. Will we run out of discoveries to make? And there's this sort of famous bad thing that physicists do, which is occasionally they get ahead of themselves and they say, any minute now, we're going to have the final answers to all of physics. So I tried to be very, very clear that that was not at all what I was saying. There is a certain well-defined subset of physics that we now understand. It happens to be a subset that includes you and me. But it does not include the origin of the universe, the asymmetry between matter and matter, the nature of the dark matter, what a black hole is, a million other things. There's no shortage of interesting questions that physicists have yet to answer. And also, of course, there's no shortage of good science questions that are not particle physics, even within physics. What about quantum mechanics? What happens when a wave function collapses in quantum mechanics? Why are there high-temperature superconductors? What can we learn about Bose-Einstein condensates in macroscopic laboratory experiments? What about everything else in science? How does the brain work? There's a friend of mine, David Gross, who won the Nobel Prize, his picture was up here, describes scientific knowledge as the interior of a sphere. So as you know things, the sphere gets bigger, but the boundary between what you know and what you don't know, which is the boundary of the sphere, also gets bigger. As we discover more things, there are more and more frontiers on which we will be working.
Thank you. I was curious if you could tell us a little bit about the detection process and specifically the detector, like what it's made of, how it works, and then kind of a side note, I was also curious as to how you deal with the data, specifically the data analysis and that.
These are very good questions. I will resist saying read my book, but that's the right answer. So it's a very good question. So because you smash protons together, particles come out. None of them have labels, these particles that come out. But you know that if you're going to detect them in your detector, the particles that come out are particles in the standard model of particle physics. Okay? So that's what you're set up to detect, and there's only a finite number of them. And many of them, the top quarks, the bottom quarks, the W and Z bosons, just decay very, very quickly. So the good news is that when you build your detector, you need to optimize your detector to detect and characterize only a small set of particles, basically electrons, hadrons, which are like the protons and neutrons and so forth, and muons. And that's basically what you're going to get. So here, the electrons, and so what you do is you build your detector in a series of concentric shells. And the innermost detector is called the electromagnetic calorimeter. It detects the photons and the electrons. Outside that, you have the hadronic calorimeter. It detects the protons, neutrons, pi mesons. Outside of that, you have the muon detector, because the muons just punch through very, very carefully. So you are able to separate out all the different particles you made, and from that, you can figure out what probably happened there at the center. That's a hopelessly, pitifully weak answer to your very good question, but that's the basic strategy. All the structure in these pictures makes sense. This is why you get these rings like that. Read the book, yeah. Go ahead.
Okay, so when the Large Hadron Collider was created, there was some rumors about it creating black holes and all that.
That's right.
So I was curious as to why that happened, why that didn't happen, why it some say it could have happened, and how that could even have happened.
Right, good. So the black holes destroying the world, the reason why you heard about it is because in, let's say the year 2007, before the LHC turned on, and you're a physicist and you're trying to explain to your friend, the journalist, why they should be interested in the Large Hadron Collider. And you say, well, there's this invisible energy field pervading space that gives mass to electrons and quarks. And the journalist is like, uh-huh. And then you're like, oh, and maybe there'll be a black hole that will destroy the Earth. Guess what the headline is going to be, the next day. And in fact, there was one guy, a slightly loopy guy, who went to court in Hawaii, because he happened to live in Hawaii, to stop the Large Hadron Collider from turning on, because he thought that they did not with sufficient care, file an environmental impact statement. Destroying the world is the environmental impact. That was eventually thrown out of court, but the idea would be, so in order to make this scenario happen, it can't happen. Why can't it happen? Because there's nothing we do at the LHC that nature doesn't do all the time. The LHC is the highest energy collisions we can make, but they're much lower energy than cosmic ray collisions hitting the atmosphere of the Earth all the time. So the idea was that at very high energies, in the standard model, in the ordinary way of thinking about gravity, gravity is very weak. You're not going to make any black holes. You just don't have enough stuff there to make a black hole. But it's possible, it's conceivable, there are theoretical models that say that gravity could be stronger than you think in these high energy particle collisions. And then you could make a black hole. And if you made it, it would decay away really, really quickly, and that would be interesting and you would learn something. But if you let yourself believe that you could make it, but also don't believe that it would decay away, well, then you would have a black hole sitting there. And maybe it would settle to the bottom of the Earth. And then you could calculate how long would it take for it to eat up and destroy the Earth. And it's much, much longer than the age of the universe. Well, but maybe you dropped a zero or something like that and you go to court, because you're a lawyer, you're not a physicist. And the physicists took this very seriously because they would die along with everybody else. We don't have like our secret underground, undisclosed location where the physicists will hang out once the black hole is destroying the Earth. But everything that we did showed there was no feasible way to reconcile what we knew with the fact that the Earth and the Moon are still here with the idea that the LHC would destroy them.
Thank you.
Yes.
Yeah. Before I ask my question, I want to thank you about bringing up that gender study, though I do have a very personal concern about that. My daughter's name is Jennifer.
Okay.
She is studying for a PhD, working for LIGO at Caltech, your school. So I now have to call her and find out if it was her CV that was used in this study.
Okay.
All right, my question is, the Higgs field is oscillating at a non-zero value. If you sum that across the universe, does that value equivalent, roughly equivalent to the mass and energy we see in the universe?
This is a good question. Before I answer it, everyone who's standing up besides the microphone right now, you will get a question answered, but then we're going to call it a day. So the answer is, so the question is, you have this Higgs field out there in empty space. It has energy. How could we compare that to the energy of stuff in the universe? Back of the envelope, the energy that you would expect is in the Higgs field is larger than the energy that we observe in the universe by a factor of about a quadrillion. So, no. This is something called the cosmological constant problem. The vacuum energy, the energy of empty space itself, is much, much, much smaller than it should be. Sorry, I got the number wrong because I was estimating badly. It's a quadrillion that it is bigger than by. So the energy in empty space is enormously smaller than it should be. Nobody knows why. It's one of the big outstanding questions in physics, yet another reason why physics is not going to be done anytime soon. Yes?
Yes, I hope this isn't too far off topic, but on the subject of black holes, it's my understanding that essentially no type of particle can escape the gravitational grasp of a black hole, but clearly gravitons can, because obviously we feel the gravitational field outside of a black hole. My brief question is, would it be possible to send some sort of theoretical spacecraft in that transmits out gravitational fields and code a signal? You could learn about the interior of a black hole from within the event horizon, which, as I understand, is supposed to be impossible due to entropy. So would that somehow be possible? Or is that
it's an excellent question, actually. And the weaselly answer, I'll try to do better in a second, but the weaselly answer is that when you say things like particles cannot escape black holes, but wait a minute, gravitons seem to because there's a gravitational field, you've run up to the barrier that you're speaking English, you're not speaking equations, right? And it's just that the language that we use, inherited from ordinary language communication, is not up to the task of getting it precisely right. The gravitons that make up the gravitational field outside the black hole are not escaping. They're there in a static configuration around the black hole. Now, having said that, when you throw somebody in, you could imagine, this former friend of yours falling into the black hole, doing things, saying, hey, look, it's a black hole, I'm falling in, and somehow the shape of what they do sends out a gravitational wave to the outside. But in fact, you can go through the math and it won't work. And this is explained a little bit in my previous book, From Eternity to Here, but The secret is that the singularity, where the black hole has an infinite density, is not a place at the middle of the black hole. It is a moment in time in the future. So your friend and everything else just smashes into the singularity, including every message that they will try to send you. Sorry.
Thank you.
Yes, hi.
How is quantum gravity different than regular gravity?
What do you know about quantum gravity? That's a very good question. So I tried to pull the wool over your eyes, and you didn't let me. So we have quantum mechanics. Gravity is clearly one of the four forces of nature, and I just included gravity in the set of forces of nature that, carried by gravitons and so forth. But you're right that gravity is not something that we understand at the quantum level. And whenever we have a set of fields, we could sort of first analyze what they would be like if quantum mechanics wasn't right. So when we understood light and electromagnetism back in the 1800s, we didn't even know about quantum mechanics, and yet we did very well. Benjamin Franklin with his kite and so forth. No one knew about quantum mechanics. We were doing classical electricity and magnetism. Newton and Laplace and Einstein were doing classical gravity. In the 20th century, we figured out how to do quantum electricity and magnetism. We tried to do quantum gravity, and we failed. So we think that there must be something called quantum gravity, but we don't know what it is yet. We don't quite know how to reconcile the postulates of quantum mechanics with the behavior of gravity. So I don't know is the answer to your question. I don't know what quantum gravity is really like. Darn you. I was doing so well up until then. All right, try to live up to that. You got a tough act to follow here.
I was just curious if it would ever be possible to detect the Higgs field outside of a particle accelerator.
So the question is, could we detect the Higgs field without using a particle accelerator, let's say, with using something else?
Yeah.
That would be awesome, because $9 billion is not coming around the pike anytime soon. So I can't say it's impossible, because if I say that, some clever person maybe in this room is going to invent a way to do it tomorrow and make me look bad. But if we could do something like that, that would be an amazing advance, because right now, after decades of thinking about it, the only way that we have to create new heavy particles here on Earth is to build gargantuan particle accelerators. If $9 billion got you the Higgs boson. If you paid half of that, $4.5 billion, you don't get half the Higgs boson. You get nothing, right? So if there were some way to do tabletop or more clever experiments that could somehow reach things like the Higgs field and the other particles of nature, that would be enormously useful to physicists. So we thought of it and we haven't succeeded yet. There's a small number of people who are still thinking. The answer might be no. The answer might be yes. One way or the other, we're going to have to be clever moving forward.
All right. Thank you.
Thank you. And thank you all.